Good morning, everyone. I am Obhirup. I am a senior applied scientist in the international machine learning team in Amazon. Today, I'm going to discuss around causal inference. So, causal inference is the study of cause and effect. So, in this field, we typically have an outcome in mind, and we want to understand that, how much is a known effect affecting that outcome. Or another related question that we might ask is that is something like at all going to affect the outcome. So what we might intuitively think of as a cause is actually not a cause. So to understand or like motivate this better, so think of the first question, which so where we from observed data, it is known that income and marriage have a high positive correlation. So in this case, marriage can be thought of as a binary variable. So zero, let's say, it represents the state of not being married, and one represents the state of being married. So if we think of the distribution of income conditioned on marriage being one, so what this basically says is that that distribution, so income is typically distributed higher when your marriage is one. So, but like, does that like mean that if someone just by getting married, someone can increase or actually multiply their earnings or income? So that obviously is not true. But then there is a then then there is a gap in our understanding that, so on one hand we are saying that, yeah, so getting married is not just getting married is not going to increase the income, but we also observe from our data that the distribution of income conditioned on marriage is higher when marriage is one. So we sort of then need to bridge this gap of the observed data and our understanding of like what is a cause and an effect, right? So so in this case, obviously the effect is sort of spurious, right? So it's not just by being married that the income is increasing, so something else is in play. And then as such, it is of importance to understand that like what is actually causing the increase in the income, or if at all getting married like has a neutral impact or has a positive impact or has a negative impact on the income. So a similar question can be that so an e-commerce platform might ask that let's say an consumer was or customer was shown an ad, and the customer went ahead and made a purchase of that product corresponding to that ad. So it might be of interest to the advertiser or to the e-commerce platform to understand that whether the purchase was made due to the ad, or the customer would have made the purchase, you know, just even without him being shown the ad, right? So if, for example, let's say he would have made the purchase without him being shown the ad, then there is so obviously then the e-commerce platform or the advertiser lost money and opportunity in unnecessarily showing the customer the ad. So it might also happen that they might want to understand that like whether there has been a negative effect due to the marketing, so which is basically showing the ad. So it is of utmost importance for e-commerce platforms and advertisers to understand these kind of questions, and in particular they would be more interested in a very specific quantitative answer to this kind of questions. For example, they might want to know that like what is the increase in probability of purchase event because of the ad, right? So they're not just interested in the directionality of the answer. So like for example, like an answer of the form that the ad had a positive impact on the purchase might be insufficient for them. So they might want to exactly quantify the increase in probability due to the ad being shown. So this is also another. So in this case, you can think of the ad as an ad as a cause, and the outcome is the purchase event. And we want to understand that, like, how did the cause affect the outcome in a quantitative sense. So another question, question, like, which is sort of similar to the first one, is that the data shows that as the number of fires increase, so does the number of firefighters. So as we can all think that, like, why this might be the case. So the fires in the historical, if those incidents have been high, the government or the policymakers would have been persuaded to uh, hire or train more firefighters, and that's sort of the reason for the increase in the number of firefighters, as that can be observed from the historical data. But and it is also of interest to like, think of ways to reduce the number of fires, right? We don't want increase in such incidences. But like, would reducing the number of firefighters actually lead to the reduction in number of fires? Obviously no, right? So it will have the uh, it probably might have the impact the other way, right? But from the observed data, or from the historical data, we would typically observe the number of fire incidents and the number of firefighters that are servicing, um, are to be positively correlated. So again, then we need to sort of bridge this gap that, like, yeah, on one hand we observe the positive correlation between the fire incidents and the number of firefighters, and we also but we intuitively understand that, like, reducing the number of firefighters is obviously not going to reduce the number of or the count of such fire incidents. So overall causal, so these are sort of some of the questions that are answered by this field of causal inference. And in general, causal inference has a extremely wide application in a lot of other fields. So it is widely applied in biology and genetics. It is widely applied in economics and other, like sociology and other social sciences, in AI and computer science, specifically reinforcement learning, um, and other, like offline, A/B testing. So there's like tons of applications in the field of machine learning and artificial intelligence where causal inference is applied. In agriculture, for designing experiments from which we can truly understand the or quantify, like, what's the impact on the outcome due to the cause. In epidemiology, in medicine, where we want to understand the efficacy of a medicine, or like whether something is at all effective, or like if something is counter effective, in public health and in management and in business and in policy making. So so in particular, in the field of data science, we see causal inference again forming a very important basis. So causal questions form the basis of almost all scientific inquiry in the data science field. So we might want to understand that if a certain treatment, in this case a medical treatment, had been applied to a patient, like, will it in general lead to more healthier patients? So basically we understand, like, whether the medical treatment has a positive impact on the patients. So similarly, a policy taken by an e-commerce platform, like, will it lead to more revenue? So those are sort of like decision making that we want to perform, and to actually perform these decision making in a robust manner, we again make use of causal inference. So in A/B experiments, where we sort of want to understand like or compare two different setups. So there also, we want to make use of, or we actually mandatorily have to use causal inference. So, for example, like if a certain ad ranking algorithm has been modified or changed, and we want to measure like what's the impact of that change. So those are typically done through online A/B experiments. And what we want to actually do is we want to quantify that, like what is the change or the improvement in like whatever metric we're measuring, for example, CTR or conversions, due to the change in the ad ranking algorithm. So in recommendation systems also, we want to understand that, like are people buying because of the recommendations that they are shown, or, like would they have bought anyway? So these are some of the questions, fundamental questions that occur in data science field very frequently. And I would guess like as part of like any experiments or any complete product or project that we do in data science, like these questions would come at some point in time. So having like discussed around like the motivations and the applications of causal inference in different fields, we now go through the outline of this particular talk. So we already discussed, or are going to sort of again touch upon like what's the necessity of causal inference. We are going to define formally like what do we actually want to, what do we actually mean by when we say that we want to quantify the effect due to a cause on the outcome. So those are known as treatment effects, and we will formalize those notions. So once we understand like that, what is that we want to measure, we sort of then describe a framework which makes certain assumptions, and under those assumptions we can devise algorithms which will allow us to make or estimate these treatment effects. And we will discuss one such framework, which is sort of like the most popular framework in like both in historical, like or like both in literature and in like recent work on causal inference. So that is known as the potential outcomes framework. So having discussed this framework, then we will actually, so this framework will allow us, or like will allow us to build algorithms on top of it to actually quantify the treatment effects. So then we will first delve into the classical techniques of causal inference, which are, although at this point, like not the state of the art, but like nonetheless they give us very strong intuition of like what is the fundamental ideas or the algorithms that can be used to measure treatment effects. And so finally we will go over some modern techniques for causal inference, so which are state of the art, or are close to it, and are obviously improvements upon the classical techniques. So we sort of once again revisit one more example of uh, like of seeing a correlated data points, but understanding at the same time that like the causation is not really uh, you know can be inferred from just the observed correlation. So in this case, if we are in a hot or summer season, So then we might see an increase in the count of ice cream sales. At the same time, we would also observe increase in the number of sunburn cases. And again, like we're interested in like reducing the count of sunburn cases, but would forcibly reducing the ice cream sales lead to a reduction in the number of sunburn cases? So that is obviously not true. So what is actually happening is that although like in our observed data, we see a positive correlation between the count of ice cream sales and the count of sunburned cases, like one does not have any causal impact on the other one. So in fact, there is one more variable, which is the weather. So in this case, the hot weather is actually causing the both of these variables to increase, right? And that's why in our historical time series data, if we could plot, then we would see that the ice cream sales and the sunburn are correlated. So so these kind of so we then just touched upon one variable, which was the hot weather, which was actually affecting both our like potential cause, so it's truly not a cause. The ice cream sales are not a cause for your sunburn, but uh, it is positively correlated with the number of sunburned cases. So a similar example could be so if we could plot the scatter plot of exercise against the level of cholesterol, then the scatter plot would look something where we would we would observe a positive correlation between these two. And if we let's say fit a regression line or a linear regression model to this data point, so where the regressor is the level of exercise and the target variable is the level of cholesterol, then we would see a regression line with a positive slope. And so which sort of so which so then that regression model effectively tells us that if you increase your regressor, your exercise level, then your target variable, which is the cholesterol level, that is going to increase. But that obviously seems counterintuitive, but because you expect your cholesterol levels to improve as you exercise more. So what actually is happening is that, so in this scatter plot, we are looking at the entire data at once, but there is another viewpoint of looking at the same data, which will reveal a different pattern. So let's say we split our data according to the age bands. So we split folks in the age group of 10 to 20, 20 to 30, and so on. And if we look at these individual groups, so we would observe that for a particular group, the cholesterol levels and the exercise have a reverse relationship. And so although overall in our overall scatter plot, there is a positive correlation, if we look into these individual groups, we see that the reverse relationship is true. And this now makes sense that like we have so within each age group, the cholesterol levels, as you exercise more, you are sort of observing the fact that your cholesterol levels are in fact improving. So which is basically decrease of cholesterol levels. So in this case, your age, so then what we are effectively doing is we are partitioning our data based on some variable. And in this case, the variable that we have used to partition our data is the age variable. And like, why did we choose age? Because age is actually one variable which affects both our cause, which is the exercise, and also the outcome, which is the cholesterol levels. So we can draw a parallel to the the hot weather or the weather variable. In this case, if we want to draw an analogy to the cholesterol versus exercise case. So in this case, if we could group together the variables according to the weather, then we would understand that like the overall effect that we are seeing is due to the presence of a variable which is affecting both the outcome and the um, cause. So, and these kind of variables are sort of then responsible for causing this spurious correlation at a global level. But when we condition on these variables, then so conditioning is a form of partitioning. So we are partitioning. So when we say that, yeah, we want to group all the or consider all the data points for whom the age is 10, so then that sort of forms one partition of the sample space. And within that partition, so conditioned on age being 10, we see that like within that partition, X and Y are negatively correlated. So then as such, like it is of very paramount importance that we are firstly aware of these variables which affect both our outcome and the treatment, and we sort of control or we sort of partition our data according to these variables. So these variables which affect both the treatment and the outcome are known as confounding variables. Um, and it's also like another interesting thing to notice is that so you could in this example you could form conditioned on your age different regression models. So in this diagram, for example, if you condition on age 10, then you or maybe like a generalized version could be you condition between age 10 and 20 and then form one regression model which is uh, uh, which models for that partitioned data, and you can form multiple such regression models, and maybe those are actually better to model like what's the change in your um, outcome, which is the cholesterol level, as a function of the change in the treatment. And this also shows that the supervised model at a global level, that if we just fitted a linear regression model to the entire data, then that is obviously an incorrect model. So you need proper partitioning. So firstly, you need proper knowledge of like what are the confounding variables and what are like, then we partition our data according to the confounding variables and then perhaps fit individual models for those partitions. But what is obviously clear is that a global supervised model would likely give us incorrect results or likely to incorrect conclusions. So a related idea is that uh, um, so in this case, what was happening is that, yeah, so a related idea is that what sort of the golden test sets that we can form to understand like what's the true treatment effect, right? And in this case, in the previous case, like there is no obvious way to measure like what's the effect of um, uh, exercise on cholesterol, right? So we are having to partition and then fit individual models, and so basically we have to perform a lot of different steps to understand that like how much is the cholesterol's changing due to the exercise levels. But a much simpler setup would have been that if we had uh, very similar individuals, so who are like come from same basically or have same health indicators in all aspects. So consider two individuals who are like twins, and they have very similar health attributes, and they are also the same age, and one of them like has a very rigorous um, or like so starting from some point in time, one of them follows a very rigorous exercise routine, whereas the other one does not. And over a long period of time, let's say a few years, we measure like what has been their cholesterol level. So this kind of like so now we can, since they were identical in all aspects except their level of exercise, so then we could just measure the difference in the outcome to conclude about like what's the effect of the exercise, right? So we can just take the difference in their outcome because they are matching in all aspects exercise except their exercise levels. So then we can uh, just take the difference in their observed outcome, and that would for like give us an estimate of like what's the impact due to exercise level. So but typically these kind of data points are not observed um, in practice. For example, like you would like your entire population will not have, for every individual you will not be able to find a twin who has like till some point in time like exactly same health attributes, and then like one twin suddenly started exercising a lot and the other twin did not exercise. So that sort of setup will never happen in practice, but nonetheless that forms a gold standard of like what's the ground truth that we are trying to measure. So what randomized controlled trials is sort of a design experiment where an entire population is split into two. So let's say there is our treatment variable is a binary variable. Uh, so so for example, if this is some medication, so then the uh, let's say there are two medications that are possible, or let's say there is just one medication, and the other group corresponds to no medication being given, or it can be that like one group corresponds to being given a medication A, where the other group corresponds to given a medication B. So in a randomized controlled trial, we split the entire population into two groups randomly. And obviously, since the partitioning is random, then the distribution of all the attributes or features across the two groups are identical, right? So at a distribution level. And on one group, we let's say apply the medication, and on the other group, we don't apply the medication, and we just observe that like how many, what was the outcome in the first group versus what was the outcome in the second group. So maybe the outcome can be defined as a recovery rate. So we observe that like how many individuals in the first group recovered versus how many individuals in the second group recovered, and the difference between these two gives us like what is the ground truth for the actual treatment effect at a population level. But as I mentioned that randomized controlled trials are expensive, time consuming, and infeasible in most practical cases. But nonetheless, this forms a like the like the ground truth or the ideal way to measure the causal impact, because like the only thing that is different across these two groups is that like one was given a treatment and the other was not given a treatment, and like every other attribute across the two groups at a population level or at a distribution level are identical. So now if so we just come to the flip side of the randomized control trial. So if something is not randomized, so which means that the partitioning that is or the treatment allocation that is happening or that is observed is based on some other variables, right? So if it was not based on anything, so then that would sort of would have been random, right? But it is not random means that like there is some amount of determinism associated with it. So which like another way of saying is that like there are some other variables which determine like that which individual is going to get what kind of a treatment. So and this leads so what like so you want to say this precisely. So what this we can say is that in observational data, treatments are selectively allocated to the individual based on their attributes. So there are some attributes which decide that which individual is going to get which treatment. And like ignoring this selection bias um, like typically would lead to incorrect conclusions about the treatment effect. So we will see one such example here. So let's say there are two medical treatments. One is called treatment A and another is called treatment B. And so the outcome that we're interested in is the recovery rate. So uh, uh, right, so it is a like for at an individual level, recovery is defined as a 0 1 variable, and recovery rate is the total number of individuals that for a subgroup, like how many people among that subgroup actually recovered. But in this case, let's say the treatment assignment is not random. So treatment A, so let's say hypothetically treatment A is predominantly given to to the population or to individuals who are of lower age group, and treatment B is given to popular subgroups who are who correspond to the higher age group. Now, as you might expect, that so if you see the treatment A's um, performance in the both the categories of for young and for old, we see that the treatment A actually performs worse than treatment B in both these age groups, right? So for young patients, treatment A has a 87% recovery rate, whereas treatment B has a 92%. And for older patients, treatment A has a recovery rate of 69%, whereas treatment B has a recovery rate of 72%. So obviously, like within each subgroup, the treatment B is uniformly better, right? But when we calculate the total or the overall recovery rate, we would observe that the treatment A has a higher recovery rate than treatment B. So again, if we just look at the global recovery rate or the global pattern, then like we are drawn to the incorrect conclusion that treatment A is better. But what we actually have to do is we have to understand that the treatment assignment in this case is not random, and it is and this discrepancy is occurring because treatment A was predominantly given to young population groups, right? So who naturally possibly have a higher recovery rate, whereas the treatment B was predominantly given to an older group, so who like possibly naturally have a lower recovery rate. So although treatment B performed well in both the subgroups, overall it had a lower recovery rate. So what we so again in this case, like our global recovery rates leads to a incorrect conclusion, and what we truly have to do is we need to find appropriate partitions to look into that, like whether treatment A was better than treatment B. And so the partition in this case is based upon age. And why is it based upon the why is age the right variable to create this partitioning? Because the treatment assignment was based upon this age variable. So treatment A was given to the population, lower younger population, whereas treatment B was predominantly given to the older population. So we again see that recurring theme that we need to partition based on the confounder variable. So age in this case is a confounder because age is determining who is getting what kind of a treatment, or is sort of like biasing who is getting like what kind of a treatment. And um, age obviously has an impact on the outcome, which is the recovery rate. So age in this case is a confounder, and we then need to perform the partitioning according to that confounder variable. So this particular phenomena, and also like what we observe here is that um like if we something, so basically there is a opposing pattern that can appear by grouping things according to certain variables. So for example, like it can happen that some batsman, so in the game of cricket, so someone has a higher average in both one days, ODIs, and in test cricket as compared to another cricketer. But so let's say the first cricketer is cricketer A, so who has a higher test average and a higher ODI average as compared to cricketer B. But the aggregated average of cricketer B can be higher than that of cricketer A. And this sort of a phenomena of seeing the opposite pattern when we group according to certain variables is in general known as the Simpson's paradox. And in the field of causal inference, so here this occurs due to the presence of these confounding variables. So now that we have studied the fact that why is it important to study causal inference, and why supervised models or like global patterns are actually insufficient to truly understand the causal effect, then we move to the next step where we formalize a framework which allows us to estimate the causal effect. So what the potential outcomes framework allows us to do is, so it provides a sufficient quantity for us to be able to quantify the causal effect. So it also determines or gives a notion of the counterfactual, or something called counterfactual. So in counterfactual question would be of the form that, like, would a patient have a different result if he received a different medication? So like possibly like would he have survived, or like would he have recovered if he would have been given a different medication than the one that was observed, or the one that was prescribed to him. So what this potential outcomes framework says is that, like, so for every possible value of the treatment, there is a potential value of the outcome. So for every medication that is possible, like, there is a um, value of the recovery variable, but we can only observe one of them in practice. And the potential outcomes framework defines, for a hypothetical intervention, the causal effect as the difference between the outcomes that we would observe with or without the treatment. So we will, like, go deep into this statement in the subsequent slides. So just before we move there, so this potential outcome framework is also known as the Rubin potential outcomes model, or the Rubin causal model. So that's um, like some different alternate nomenclature that is used in the literature. So this potential outcomes framework is the most popular and also, like, the most adopted one in the modern literature in the study of causal inference. So just to formalize what we were discussing the previous slide. So let's say we have a treatment variable T. So which in this case, let's say, denotes the medication being taken or not. And so the outcome is that, like, whether after taking the medication, the headache was reduced or not. So the headache is like denoted by the variable Y, and the medication being taken or not is denoted by T. And we ideally want to understand this impact for every individual, right? So I is the index or subscript corresponding to the ith individual. So yi0 then denotes the potential outcome under, sorry, there is a typo here. So yi one denotes the potential outcome under treatment, and yi0 denotes the potential outcome under like no treatment. But in practice, what will happen is that, like, once we have a headache, we will either take the medicine or not take it. So let's say we did not take the medicine, we chose not to take it. So, and then we observed that the headache did not go away. So in this case, what we actually observe is that, like, we observe the yi0, and we say that, yeah, yi0 is 0. But in this case, we would not be able to say that, like, if had I taken the medicine, like, would it have been effective? So in other words, like, is my yi1 actually 1, or like maybe yi1 is 0, maybe the medicine is not effective. So, but like, whatever is the value of yi1 is like, not known to me, because I chose not to take the medication. So this is what we call as the factual observation and the counterfactual observation. So either, like, I would have taken the medicine, and I won't know the possible outcome or the potential outcome that would happen in the case of, like, if I hadn't taken the medicine. And similarly, the vice versa, like, if I did not take the medicine, I would not know that, like, if I had taken the medicine, like, would I have potentially like, cured of the headache. So in general, so if you look at the right hand table, so for the first when I is 1, that is the first patient, so he did not take the medication, and, like, his headache was not cured. But what we don't know is that, like, whether what would have been his value of yi1, right? But we know that, like, yi0 for him is 0. And so for the second patient, he took the medication and he was cured. So for him, yi1 is 1 and yi0 is unknown because we don't know what would have happened, like because he took the medicine, so we don't know his case for or the case where what would have happened like if he did not take the medicine. So likewise, so one thing to observe is that, so like for every patient, then we either observe one of the two possibilities, right? Because the other one is a counterfactual. So we haven't, there is no factual observation for those applications of treatment. And as such, since one of them is always missing, the we cannot factually observe this difference of yi1 and yi0, right? So ideally what we would want to know is that, like, what if I take the aspirin, like would the headache be cured? So what effectively we're trying to understand is that, like, which are the data points or which are the individuals for which yi1 minus yi0 is equal to 1, right? So those are the sort of the effective cases. So because, like, if your so think about the case where yi1 minus yi0 is 0. So it can happen if your yi1 and yi0 both are 1, or both are 0. So both are 1 means that, like, irrespective of the medicine, someone was cured, and both are 0 means that, like, irrespective of the medicine, that person was not cured. So those are individuals for which the medicine was not effective. Whereas the case where yi1 minus yi0 is 1 are the individuals for which the medication was effective, or is potentially effective. And we want to sort of find out, like, yeah, for how many individuals like these things happens, or like on who are the individuals, so then we can go ahead and prescribe them the medication. But in general, like, just from observed data, this thing is not possible to be um, directly observed or estimated. So we would need specialized methods to actually find out this difference. And then this table, if you, this is sort of like the fundamental question that we are asking in causal inference, is that, so we have observed data of this form, basically this pair of t and y, and so t is in this case, or in general, like, it not randomly allocated. Okay, so t is allocated to individuals basis some other variables, which are the confounders. And now under this setup, we want to find out, like, what is y1 minus y0 in case of a binary treatment. And this thing is called the treatment effect. And this forms the core of the, like one of the fundamental problems in causal inference, that we want to find out this treatment effect. And and the rest of the talk, we will go into details of about algorithms which will allow us to do that. So having discussed the framework for potential outcomes, and also discussed around, like, what's the fundamental problem that we are interested in solving for causal inference, we look deeper into the data generative process. So the table that we were observing in the previous slide, that can be thought of as having been generated from uh, such a data generative process. So we have the treatment variable ti for the ith individual, and then we have some features, or some variables xi, which affect, like, that which treatment is going to be allocated to which individual, right? So basis, like, what are these features, like, is age, gender, demographics, other demographics, then some particular treatment is going to be assigned to the ith individual. And now this both the treatment and these features are going to affect the outcome, which is generated by yi. And according to the potential outcomes notation, yi is actually a function of ti. And obviously it's a function of xi, but for brevity, that is like we don't directly write it. So what we want to write is that, so for every value of ti, there is a potential value of outcome, and that is denoted by yti. And our entire data can, for example, like in this table, so it can be thought of as being sampled in an IID fashion from such a graphical model. So we have triplets of the form xi, ti, yti, where xi are the confounders, ti is the treatment, and yti is the observed outcome corresponding to that treatment. And the individual data points are sampled IID from this graph. And we are interested in finding out not only, so the YTI is observed, but what we are actually interested in finding out, like what is the value of YTJ, or maybe we're interested in finding out what's the difference between YTJ and YTI, where TJ is another treatment, which is different from the one that is observed. So that there is a fundamental difference of in the data generative process in this case, where selection bias is present versus the case of supervised models. So in supervised models, what happens is that we have an outcome variable, which is typically known as the target variable, and we have features, and maybe we have so our data points are again of the form xi, ti, yi, where ti is some so ti is again a treatment, but the interesting thing to note is that, like, it is not the treatment in this case is not determined or affected by the features. So there is no arrow joining the features to the treatment in the case of supervised learning. But in the case of the causal inference models, the treatment assignment TI is actually a function of the features xi. And in the supervised learning setup, we want to model yi as a function of xi comma ti, right? And we are not interested in the question that, like, what is what would have been the value of yi, or what would have been the value of y had we changed ti to tj, right? We are not interested in knowing that. We just want to know that, like, yeah, ti is the observed treatment, or ti is the usual treatment, and like what's the best estimate or predictor for yi in that setup, right? So in the supervised learning setup, we are not asking a counterfactual question. Our test rate distribution is the same as our like what we have observed in the training data. So we are not trying to deviate from what is typically observed. We are just sticking to that, and in that setup, we want to find out, like, what's the best function estimator if that we can find to estimate yi as a function of xi and ti, right? And finally, like, yeah, so as we already discussed, like, ti's are not determined by the rest of the features xi's, right? So an example of, like, very, like, most, like there's tons of examples of supervised learning, for example, forecasting, image classification, and so on. So they are, like, your like, for example, in your image classification, if you have an ImageNet kind of a data set and you just split it randomly into test and train, then your train distribution is, sorry, your test data distribution is not fundamentally different from your training data distribution, right? And it just your task is to find the best fitting function where I mean, obviously you have different notions of what's the best fit, but what you effectively want to do is you want to fit your data and perform smooth extrapolations. So that's like your typical, that sort corresponds to typical supervised learning. So a related field is or another very popular field of machine learning is reinforcement learning. So where so there is an underlying Markov decision process. So there we in a MDP we would observe some rewards. So the rewards analogy in this case are the outcomes, right? So your headache reducing or recovery is sort of like a reward, and the treatments are the actions that are undertaken in a Markov decision process, right? So the treatments are analogous to the actions in a MDP terminology, and XI is what is typically known as the context. So or the state features in the MDP terminology. So although so now in a Markov decision process, what we will do is we will sequentially observe that like what was the state, what was the action that was taken by being in that state, and due to that action and like being in that state, so being in that state and like then taking that action, like what was the reward that was observed. So even in the case of reinforcement learning, we typically observe our data points to be in the strip, like in the form of these tuples of xi, ti, yi, where xi is your state vector or the state features, TIs are the actions that you have taken, and YIs are the rewards that you have observed. So the fundamental difference between this data generative process and the causal inference process is that like here your data is generated sequentially. So it is not sampled IID from this graph, right? So your subsequent, or in particular your subsequent data points are very positively correlated because your next action is so if you yeah so your obviously your state, so next state is dependent on like what was your prior state, right? And the next action maybe is like depending on what algorithms you are using is maybe dependent on like what was your past action. So as such, your state variables and your actions are not necessarily independent, but your subsequent like your like data points are correlated because of the temporal structure. And in there is not only a temporal structure, there is also a Markov structure of some form that is assumed. So what that means is that your future state or the next state depends only on the current state and not the entire history of of the states that you have traversed to reach the current state. So this is typically this is so what I described is sort of like the Markov of order one, but in an MDP, like so some form of Markov. So it is assumed that your state transitions are follow Markov structure of some order k. So again, like in this way, the reinforcement learning, the data points that you would observe from such a model, have been generated in a different way as compared to the causal inference graphical structure that we studied. And also another difference is that like in reinforcement learning, you don't necessarily want to model yi explicitly as a function of ti, right? So you are not interested in like yi ti kind of a function. So what we especially in model free reinforcement learning, what we want to do is we want to like find out actions which such that the action trajectory leads us to a long-term benefit or a like long-term maximization of your rewards. So in that sense, there are like two differences with reinforcement learning with respect to the optimize or the objective that we want to achieve. So one is that like we don't necessarily model yi directly as a function of ti. So maybe like you can think of your the q learning, so where you learn the QSA functions as a like directly learning q as a function of a. So you can plug in different values of a and obtain different values of QSA. So that is one form, but like in a policy gradient based method, like you will just obtain like what's the best policy to take. So you will just find a distribution over the TI space conditioned on your context xi, such that your long-term return is maximized. So there you are not effectively modeling like what is the different potential values of your outcome uh, given the action, right? So yeah, so and also the other thing to note is that like in supervised models and both in causal inference, we are trying to predict yi, right? But in reinforcement learning, we're not trying to predict or optimize for the immediate yi, but we want to maximize the sum or discounted sum of yi over the episode length. So that's another difference in with respect to reinforcement learning. So just to close off this discussion or close off this similarities and dissimilarities with reinforcement learning. So we see that like the similarities that the action is actually dependent on the state. So the state actually also affects what's the outcome, obviously, right? And the action also affects like what's the outcome. So the state is in some sense a confounder. But like having said that, like the rest, all the things are very different. So there is a like firstly like your xi ti yi's are not sampled IID. There is a Markov structure, and you don't necessarily model yi as a function of ti directly in model free RL. And your optimization objective is to maximize your like discounted sum of yi's. So now having like discussed supervised learning, causal inference, and reinforcement learning in the abstract sense with respect to how their data generative process looks like, we just go over some concrete examples of each one of them. So like classic examples of supervised learning is predicting the future temperature. So basically forecasting model. So there is like we are not performing any intervention. So for example, like weather prediction, like yeah, like even if we want to intervene, it is like not possible to or natural or easy to do that. So we can predict the future temperature as a function of historical temperature, humidity, and so on. So in causal inference example would be an uplift modeling. So this branch of modeling deals with estimating the consumer demand as a function of change of price. So for example, like if the price of a ride sharing app increases, like would the consumer demand decrease? Same for a e-commerce, like similar for e-commerce platform, like if the the price of the product increases or the discount of the product decreases, like would people start buying more or less of that product? And reinforcement learning is basically examples where we learn a sequence of steps to ultimately achieve a long-term goal. So like the very infamous the famous AlphaGo algorithm learns to play a sequence of moves to win the game of Go. Having discussed the fundamental problem of causal inference and its difference from supervised learning and reinforcement learning, we concretize the exact estimates or statistics that we want to find out. So these are called treatment effects. And a treatment effect can be measured at a population level, at a treated group level, at an arbitrary subgroup level, or at an individual level. And depending on the context, it might be of importance to measure the treatment effect at different levels. For example, for a personalization application or a personalization recommendation algorithm, it is important to understand the effect of the treatment at an individual level as well as at a population level. So perhaps for a recommendation algorithm, it is uh, uh, like more important which to understand the impact at a population level, that is like what is the global or the overall increase in revenue due to the improved recommendation algorithm. Whereas for a in a medical system, it might be of more importance to understand the treatment effect at an individual level, because we want to provide the best medication possible for every individual, and it is not always sufficient to perform um, like just to do or improve the overall numbers. We ideally want to provide every individual with the best possible treatment for him or her. So for a binary treatment T, so binary treatment T means that it takes two values, 0 and 1. Um, we defined what is called the average treatment effect, which is a population level estimate. So it is the difference of the expectation of the potential outcome if we would have if we would give the treatment 1 versus the treatment 0. So empirical estimate of this ATE, or the average treatment effect, is that for if we could hypothetically compute like what is y1 and yi1 and yi0 for every individual, for the ith individual, for all I, and then take the difference, then that would give us an estimate of the ATE. But as we had discussed in the notion of counterfactuals, that for the ith individual, we can only observe either yi1 or yi0. So we don't like have an empirically observed estimate of ATE, and we will need some sort of a model to learn this difference, or perhaps try to estimate like what is the value of y1 and yi1 and yi0 for the ith individual. So that can be another approach perhaps. So at a arbitrary group level, so if if the calligraphic X denotes an arbitrary subgroup in the population, then the conditional average treatment effect, or CATE, can be defined as the difference between the potential outcomes when the individuals are taken from that particular subgroup. So for example, like we might want to understand that what is the effect of the medication on males, for example, or what is the effect of of a particular medication on elderly folks. So we might have some interest, we might have an arbitrary subgroup X, and we want to find out the treatment effect when when the treatment is potentially applied to all the individuals in that subgroup. And finally, we have something called the individual treatment effect, which intuitively, as we might expect, the definition is just yi 1 minus yi 0. And in that sense, the individual treatment effect is a special uh, case of Kate where the subgroup is just consists of that individual. So so primarily so these are so ATE, CATE and ITE are typically the things that we are interested in terms of understanding the treatment effect. So the potential outcomes framework also provides us with a set of sufficient conditions under which we can actually obtain robust estimates of the treatment effects. So in next, we are going to learn about these assumptions and also like why they're important, and also learn about situations where these assumptions might get violated. So we will have to be careful in understanding that the potential outcomes framework comes with some limitations and like and in what practical settings they can actually be applied, and where it would be incorrect to directly apply it. So the first assumption in the potential outcomes framework is known as the stable unit treatment value assumption, or SATVA in short. So what this assumption effectively says is that the outcome for any unit does not vary with the treatment that is assigned to another unit. So consider the example that one patient's treatment is not going to typically affect what is the outcome for another patient, right? So the treatment for the ith patient is only going to affect the outcome for the ith patient, and it is not going to affect either the treatment for the jth patient where j not equals to I, and it is obviously not going to affect the outcome for the jth patient. So one classic case where this or scenario where this stable unit treatment value assumption does not hold. So consider the treatment. So in an e-commerce platform, consider the discount as being a treatment. So discount, let's say, can have values of some discretized percentage. So it can be 5%, 10%, 15%, 20%, up to some upper bound. Uh, and sorry. So every product, let's say, has some discount value, and the outcome that we're interested in is the conversion or the purchase event. So let's say or the purchase rate, which is uh, the count of purchases that have happened divided by the total number of views of that product. So now, if there are two very similar products and one of them has a very high discount, then uh, then uh, customers are very likely to go ahead and purchase that product, right? So then they will not be inclined to purchase the substitute or a very similar other product because it has a one has a much lower price than the other because of the amount of discount that is given. So in this case, what is happening is that for the ith product, if it has a very high discount, and if the jth product is a very similar product to the ith product, then the outcome of j, or the purchase rate of j, is getting affected due to the treatment of I or the discount of I. And this is a situation where this stable unit treatment value assumption does not hold true. So what actually is happening in this case is that if we could think of a group of similar products, but then like what is so the outcome for each one of them is dependent like on not only the discount that is available for that for itself, but also on the discount that is available for the other products which are very similar to it. And this is like a strictly a much harder problem to solve than the case where like each individual treatment is not going to affect the outcome of the others. So the next important assumption is known as ignorability. So which says that conditioned on the confounders x, the treatment assignment or the treatment variable t is independent of the potential outcomes. So what it is saying is that like if we condition on the confounders, then the potential outcomes are becoming independent of the treatment assignment. And so we saw a flavor of this thing when we were partitioning. So effectively what it is inclining is that like once we partition according or once we condition based on these confounders, then we can truly understand like what is the so then our treatment assignment is sort of replicating that of the randomized control trial. And in that setting, in that sense, we can better understand like what is the true treatment effect. So this result is nothing but a consequence of what is called the dispersion theorem in probabilistic graphical models. So if we so we had observed like the what was the graphical or data generative process for the causal models, and once we apply the dispersion theorem on that probabilistic graphical model, we arrive at this result of ignorability. So this result is also known as unconfoundedness, or the fact that so which indicates towards the fact that like we are aware of all the confounders, that is we know all the variables which affect both the treatment and the outcome, and all the confounders are known and that we can actually measure them. So example of ignorability is that so in the Simpsons paradox example, we observed that like age was the only factor that was determining the allocation of treatment. And once we controlled for that, we were able to actually find out the correct estimates of ATE. Uh, uh, and so if age like if we, so in that case like we were both able to know that like what was the confounder, and we were also able to measure it for every individual. So a typical case of where this ignorability will not hold is where we have an unobserved confounder. So consider the outcome, or consider the treatment as being like having an university education, and the outcome as getting a job. So university education can be thought of as a binary 0-1 treatment, and getting a job can also be thought of as a 0-1 outcome. And now the socioeconomic background of an individual determines whether he or she actually is able to obtain a university education, right? And obviously the socioeconomic background also determines like that in the future, like whether he or she is able to land a job. And the treatment, the university education also influences the likelihood of getting a job. So this is a classic case where we where the socioeconomic background is impacting both the treatment and the outcome. But if you think of socioeconomic background, like it's a sort of a vague notion in the sense that like there is no single measure or a set of statistics that we can uh, write down, which will guarantee that yeah, like we have captured every aspect of socioeconomic background. So what instead we have are sort of proxy measurements about the socioeconomic background. So we, for example, can take the parents' education level, we can take the family income, and so on. But what these variables are essentially, these are noisy observations from the true confounder, which is the socioeconomic background, but there is no good way for us to even define or measure that, right? So we can only observe or measure some noisy observations, or proxy observations for that. And in that setting, since we do not observe the true confounder, um, we are no longer in this strong or this ignorability setup or the unconfoundedness setup. So as I was discussing, so the implication of ignorability is that for units with the same value of confounder x, their treatment assignments can be viewed as random. So which is effectively saying that, like, if we properly partition according to the, or just partition according to values of x, then within those partitions the treatment assignment is kind of replicating an RCT. So which is just a mathematical way of writing that for two individuals with the same confounders, it is the probability of the treatments is same. So the third assumption in the potential outcomes framework is that of positivity, where we say that the treatment assignment is not entirely deterministic and there is some amount of randomness associated with it. So while it is exactly not a randomized control trial, but there is some amount of randomness associated with the treatment allocation. So so what that means is that for any value of x, the treatment assignment, so it is not a degenerate distribution. So it just doesn't give like the mass to one of the treatment data points fully. So the ignorability and the positivity assumptions are together called the strong ignorable um, assumption. And so this positivity is also analogous to the non-deterministic behavior policy in a off-policy reinforcement learning setup. So what that means is that there is some amount of exploration. So in an off-policy reinforcement learning, you will typically observe data from a behavior policy and try to learn the optimal policy from your observed data generated from the behavior policy. But if your behavior policy has a typically if it has a very limited exploration, then learning an optimal policy in an off policy setup becomes difficult. So analogous to that, in an causal inference setup, if the treatment assignment is very deterministic, then it causes a problem. So and as such, like it is ideal that if we have some amount of randomness, however small that is, present in the treatment assignment. So to illustrate with an example, so let's say uh, in the Simpsons paradox example, if so there were no individuals of age group 10 who were given treatment, or there were no young individuals who were given treatment B, right? And it was only given to older folks. So then we wouldn't actually know like what would happen to the young folks when they are exposed to treatment B, right? So there's actually no way to extrapolate that information from the data points based on just the older folks. So so what we would want is that for young folks, there is a like at least a slight probability of it getting the treatment, like both getting slight probability of getting both treatment A and treatment B. So given these assumptions, we focus on four methods of estimating the treatment effect. So there are reweighting methods, stratification based methods, in representation learning based methods, and tree based methods. So we initiate with a very important and a classical way of estimating treatment effect, which is the propensity score based reweighting. So in this method, what we do is for every individual, we calculate this. So let's say we are in a binary treatment setup, and we calculate something called a propensity score. So the propensity score is defined as the likelihood of obtaining, let's say we are in a binary treatment setup. So the probability of obtaining the treatment t equals 1, given the value of the confounders. And an important result is that, so we had observed in the case of the condition of the assumption of ignorability, that the treatment is independent of the potential outcomes conditioned on the confounding variables. So an corollary to that result is that if that is true and positivity is true, positivity assumption is true, then the treatment assignment is independent of the potential outcomes given the propensity score. So the propensity score can be thought of as a random variable in itself because it is a function of x. So we so instead of partitioning by values of x, so x actually can be sort of high dimensional, right? So we were trying so partitioning based on that random variable or conditioning based on that random variable is difficult, but the propensity score is actually a scalar. So partitioning or conditioning on that is much easier because we just have to create some discrete bins or some heuristics, simple heuristics to partition this scalar random variable. So the approach of propensity score based reweighting is that we use any machine learning model to model this propensity function or the propensity score function, which is this E of x. And and now to every data point, what we want to do is that we want to give it weightage inverse to its likelihood of, like having observed the treatment. So to understand like the intuition behind this inverse propensity scoring is that, so let's say we want to understand, so again, we go back to the Simpson's paradox example. So treatment A was primarily given to younger folks, and treatment B was primarily given to older folks. But we also observed positivity in that case, so that so there were some young folks to which treatment B was given, so although that number was small, and there were some old folks to which treatment A was given, so although that number was small again. So what we want to do is, so now the young folks to whom treatment B was given, so they are valuable in some sense, right? Because they form a rare sample, because like most of the young folks have been given treatment A, right? And treatment B has been given to most of the older folks. So the young folks to whom treatment B has been given are valuable. And in the same way, uh, the older folks to whom treatment A has been given are valuable. So from these two groups, we can possibly try to understand that, like, what is the impact of, let's say, giving treatment B to young folks, and what's the impact of giving treatment A to older folks. So although these are like sort of very sparse or minor regions in terms of like density of the treatment allocation, they are very important because they are in a way representing what are the counterfactuals. So for treatment B, for most individuals, we will see that it is given to older folks. And um, right. So yeah, so coming back to this thing, so it's so since these two segments of the data form rarer groups, and they sort of answer the counterfactual questions, so it is important that we give more weight to these particular groups, and that forms the basis of this inverse propensity scoring. So if you see the score function, so it's basically saying that like how likely someone is to get the treatment 1. So if the treatment t equals 1 corresponds to the treatment B in the Simpson's paradox example, so then when x is young, then that p of t equals 1 is very low, right? Because young folks were predominantly not given treatment B. So what we want to do is like we want to sort of give or consider them more seriously, or give more weightage to those points. So I will come to like how this weightage is used, but just for now, just think that like we are giving more importance to those data points, or we want to be keep a close eye on those data points. So that's what like giving more weightage to those data points mean for now. So so once we have given this inverse weightage, so the ATE estimate can be defined as the sum over all data points, and we multiply the TI with YI and divide it by the uh, or multiply it by the inverse of the propensity score. So TI, so now if we consider this sum over all the data points, so for so this sum will only have non-zero values where Ti is 1, right? So for all the points for whom the treatment 1 was observed, we calculate this quantity, the first term, and what we do is we take the observed outcome and divide it by the likelihood of getting the treatment 1. So points which are very unlikely to get the treatment 1, so their YIs are scaled much higher. So you can think of that like, yeah, we are giving more importance or considering sort of like replicas of those YIs. And similarly for the other case where TI is 0, we give more weightage to where to the points where 1 minus E of xi is low, so which means that E of xi is high. That is priority of t equals 0 given xi is low. So which is the same idea that we were doing here. So this is a final estimate of ATE that we obtain in the inverse propensity weighting method. And so effectively what we need to do is we need to train a machine learning model to estimate this E of xi, and then we calculate ATE in this way. And this is obviously, and this method is better than using the just a simple difference of the observed values. So inverse weighting sort of creates a pseudo population in which there is no confounding, so that the weighted averages reflect the average that would have been observed if we were actually operating in an RCT setting. So to understand this slightly better, we need to understand like what is importance sampling. So importance sampling is a core idea in sampling theory, where we want to calculate expectation of a random variable with respect to an arbitrary distribution. Okay, so so the idea is that so let's say we are given an IID sample y1 to yn, which is naturally coming from some distribution G, right? And we want to calculate the expectation of some function f of y. So, by f is a known function. So let's say f of y can be y squared or mod y or anything. So we just need to be able to compute f of y given y. And now we want to calculate this expectation of f of y not under the natural distribution g, but we want to compute it under a different distribution h. So hypothetically, if y1 to yn had been drawn from h instead of g, we want to calculate the expectation of y under that setup. So to do this, so we start off with, so we want to calculate the expectation of f of y with respect to h. So if we take the density of h to be small h y, then we can see that this expression by introducing g of y, where g is the density corresponding to the original distribution g, we can say that it is equivalent to calculating the expectation of hy by gy times fy, right? Where the data points are sampled from the original distribution G. And now for this quantity, so all we need to do is we need to be able to write down what is hy, what is gy. And if we can do that, then we can always calculate this expectation. So think of that like y, initially, let's say y's were drawn from some normal 0, 1, and you want to calculate the expectation of y square, and your h is some other distribution, for let's say Cauchy. So yeah, I guess like the expectation might not exist for Cauchy, but so let's say you want to estimate it under exponential. So h is an exponential, and then g is your normal. So you can sort of write down like what is h of y and what is g of y, and as such you can calculate like for given y what is this value of hy if by gy times f of y for every y. And so once you do that, you can so since this expectation with respect to the original distribution g, we can take a Monte Carlo sample, Monte Carlo estimate to finally approximate this integral, which was our original objective of obtaining the expectation of f of y under h. So in the relationship of this importance, so what the importance sampling this trick does is, so we take our function fy, right, of which we are trying to find out the expectation, and we multiply it with the ratio of the two densities, and then just take the Monte Carlo estimate. So that's our importance sampling technique. And so if you draw the connection with the inverse propensity weighting, so what we want to do is we want to find out like what is our expectation of our ITEs, where the distribution H is that of a random distribution. So we want to mimic the RCT. So in an RCT, your probability of t equals 1 given x is equal to probability of t equals 0 given x equal to 0.5. And your g of y is the original distribution, which is the propensity score. So you have your and your f of y is the observed difference. So not the difference, but it's the outcome, right? So so in that sense, your e of xi corresponds to the g of yi here, and since it's a since h is a Each is corresponding to a random, corresponding to a RCT setup. So it is just 0.5, so it's sort of constant, so it is not present. So effectively this becomes f of yi divided by gyi, so which is the expression that we see here. And ti multiplying by ti just to ensure that we are taking the points where the t equals 1 is observed in this case, and we are taking the points where t equals 0 observed in this case. So that's the intuition behind inverse propensity weighting. But inverse propensity weighting, also note that it is a good way to estimate ATEs, but it is not a good way to estimate ITE, because as you might imagine, that this at an ITE level is a low bias and a very high variance estimator. So there is a further improvement that is possible for the inverse propensity methods, which is known as W robust estimation. So in this methodology, we aid the inverse propensity weighting method with two regression models. So we build a regression model to directly predict y as a function of x and t equals 0. And so what we do is, in a binary treatment setup, we we train two regression models, m0x and m1x, which are estimates of expectation of y given x equals x, t equals 0, and expectation of y given x equals to x and t equals 1. So these are just supervised regression models. And then what we can do is we can define a W robust estimate in this way. So which is the inverse propensity model estimate plus some additional components which are based on the regression models. So what we can show is that if like even if in the previous case, the E of xi was a supervised machine learning model which was predicting the propensity score. And in this case, so we have three models. So one is the E of xi, represented by E of xi, and then the other two are m0x and m1x. So what we can show is that, like, even if like either the regression models are correct, or are like the true regression models, or the propensity model is correct. So if either one of them is correct, and like even if the other model is incorrect, so even in that case, this doubly robust DR estimate of ATE is a consistent estimate. So consistent estimate means that, like, this converges in probability to the true treatment effect at the population level, or the true ATE. So the result is that, like, it is unbiased if like one of the models, like, so one of the classes of models, I should say, actually. So even if, like, the regression models are correct or the propensity model is correct, then this DR estimate is an unbiased estimate of the true ATE. So this is like, again, a lower variance and lower bias and high variance model as compared to the inverse propensity weighting models. So we next move on to a grouping or a matching kind of a technique, where we split the, so we in the very first few examples, we were seeing that, like, we were partitioning our data space in based on, like, what was the values of the confounder x. But we also later observed that it is sufficient to partition according to the propensity score, right? We don't necessarily need to partition on a high dimensional x. We can perhaps partition based on the scalar E of x. And that's what the subclassification methodology is based upon. So what we do is we split the entire population into homogeneous subgroups, such that within each subgroup, it sort of like replicates an RCT. So what we first do here is we train a supervised model Just in the case of IPW, we train train a machine learning model to predict like what is E of x. So once we have E of x, then we perform a quantile binning. So since E of x is a scalar and a probability, so it takes values between 0 and 1. And we perform quantile binning to sort of create these partitions of E of x. And within each quantile bin, we look at like what is the value of points which are for which t equals 0. I mean, basically we calculate like what is y I1 and yi 0 for every data point in a bin. And then we can like take the difference of the yi1 and yi0 within a bin, because within a bin the treatment allocation is random. So then we can take the difference in that bin, within a bin of yi1 and yi0s, and like take an overall average to calculate ATE. So subclassification is a technique which is specifically suited for binary treatment. So the IPW and DR, so they have natural extensions into multi-treatment setups or even continuous treatment setups. So there we just define, we can define a generalized propensity score, and still since the idea is based on the importance sampling theory, so it can be extended, like it doesn't necessarily need, so as you could understand, like there is no restriction on like what H was, right, which is the target distribution. So it works effectively where like in like we don't need to modify the theory to apply it to like higher dimension, higher cardinality treatments or to continuous treatment case. But subclassification is a technique which is specifically suited for binary treatments. So what we do here is, as we sort of discussed, that we create quantile-based bins of propensity scores, and we estimate the ATE as the the difference between y1 and y0 within each subgroup, and where nj is the count of treatment points in the jth group. So, so the subclassification estimate converges to the. So now, if you look at this expression, so let's consider. So for the so let's consider this the leftmost bin. So what is happening in that is that like that the most of the points are likely to go to treatment t equals 0. So control means actually t equals 0 and treatment means t equals 1. So the most of the points are actually likely to go to t equals 0, and we see that like due to positivity assumption being true in this case, there is some amount of points which are actually belonging to treatment, even although like based on its confounder values, ideally it should have been or it is highly likely that it would have been actually a control or assigned to control. So so for that leftmost bin, so we see that so y1 so y1j is the mean of the outcomes for treatment type 1, right? So in this case, it's basically the average of these purple points, that is y1j, and y0j is the average of the outcomes for these red points. And we see that like both y1j and y0j are given equal weightage here. So in other words, so although y1j is comprised of much less number of points, these purple points, and y0j is comprised of much more number of points, so finally they are given equal weightage. So in that sense, these purple points are given a aggregate higher weightage, right? And that is again very similar to the notion of the inverse propensity weighting, where we were giving the rarer occurrences of treatment higher weightage while calculating the the ATE. So the subclassification technique also will converge to the IPW estimate in the limiting case where the limit of the number of bins goes to infinity. And to draw its analogy to the doubly robust estimation case, what we can do is we can not only bin the data points into these quantile based bins, we can also and take the simple difference like y1j minus y0j. Instead, we can build a regression model m1j and m0j, which estimates y1j and y0j in a more smooth manner, perhaps, and use this estimate, the sum over j of nj times m1j minus m0j. And we can show that again, like as the number of bins goes to infinity, this estimate approximates the doubly robust estimate. So subclassification overall gives us a very nice geometric interpretation and very intuitive way of understanding like what is happening, like or how are we actually arriving at the ATE estimates, while having the property that like we can increase the number of bins to get close to the IPW estimate. So one thing to note is that like if we arbitrarily increase the number of bins, then like there might be some bins where there is just one type of treatment or control, and in that case we are sort of possibly violating the positivity assumption. And in that case, like this like if there is only y1j in some particular like bin, then this y1j minus y0j is not defined for that bin, right? We cannot factually calculate that. So that also becomes a problem. So that's the main issue with arbitrarily increasing uh, the number of bins. So in general, like increasing the bin count will lead us to a low bias but high variance estimate of ATE. So we, having discussed a subclassification technique, we next move on to some of the modern methodologies of estimating the treatment effects. One such methodology is based on like obtaining balanced representations of the confounders for the different treatment types. And one of the seminal papers or work in this field is of that of the methodology which is goes by the name of TARNET, which represents treatment diagnostic representation networks, and a very related technique of balancing neural networks. And this line of work is in general heavily motivated by the domain adaptation models. So in domain adaptation, we have training data from some particular domain, and in our test, we want to predict it for some other domain. So which is sort of like what we are doing even here, that our original data is generated from some selection bias inducing method, and we want to actually move to a or predict in an RCT kind of a setup. Like although we don't have like ground truth data for RCT, like that's our target distribution. So in that sense, there is a lot of similarity of causal inference with the domain adaptation models, and the balanced representation learning methods heavily draw inspiration from the domain adaptation based models. So the Tarnet model defines something called a factual and counterfactual loss. So the factual loss is nothing but, so let's say you have some loss function. Let's say it can be squared error or cross entropy, although like the theoretical results for Tarnet are valid only for MSC kind of a loss. So let's say you draw from the natural distribution of P of x given t, and then try to predict the factual outcome for the data points drawn from the natural distribution. And so in the other way, we can also draw from the case where t is not equal to the naturally observed treatment, and we want to still calculate and evaluate our loss function in those settings. So that forms the motivation for the factual and counterfactual losses. So now the counterfactual loss is actually not, we cannot go ahead and empirically estimate this. So for factual loss, we have a Monte Carlo estimate, which is your typical. So if L is a MSC loss, then we can obtain a Monte Carlo estimate of E of F. But for E of CF, which is the counterfactual loss, we cannot obtain a empirical Monte Carlo estimate, because we are sort of like intervening and changing the the loss, right? So we still draw from the natural draw the data points x comma t from the natural distribution, but we now go ahead and intervene in the treatment variable. So just as we were trying to like understand what is our what's the ytj, for different tjs, for different j's, where j not equals to I. So here also, like, we are trying to find out like what is L of x t prime, where t is not equals to t prime, where t is the natural treatment. And obviously, like, now all these L of x t prime, we cannot factually observe, because we cannot factually observe like what is y t prime. So we can only observe what is yt from factual data. So as such, what this Tarnet paper does is, so it forms and gives us an upper bound of EF plus ECF, and that upper bound can be calculated empirically from data. So the result of the paper is that this upper bound is given by a weighted function of the factual loss, and another term which is called the integral probability metric, and which is a sort of like a distance metric of our distributions, and it calculates the like how far are the confounders when we are when the treatment is 0 versus when the treatment is 1. So if you if you think of so if your treatment is like going back to the example of the Simpson's paradox. So we want to understand that, like, what's the age distribution. So P of x given t is the age distribution given the treatment. So for the treatment A, like, what's the age distribution, and for treatment B, what's the age distribution, and how far or how similar are they. So if they were actually exactly similar, then we are in an RCT kind of setup. And if these two are very far, then we have like, we are further away from RCT, right? So So that's basically the idea here. So then IPM, or the integral probability metric, is a distance or a proper metric for distributions. And in this case, the result of the paper is that the sum of the factual and the counterfactual losses can be upper bounded by alpha times the factual loss plus beta times this IPM. Uh, now, now this IPM can be calculated for a sample. So there are like different ways of estimating this IPM, and the factual loss, weighted version of the factual loss can also be calculated. So we first delve into like what is sort of an IPM, and like how can we calculate a sample estimate of uh, that this IPM of for any arbitrary distributions P and Q. So consider two distributions P and Q, and let's say we have observed data points x1 to xn from P and y1 to yn from Q. So for simplicity, let's say these are all like one-dimensional distributions, and like the blue curve here corresponds to the density of the points or density corresponding to the distribution P, and the red curve is corresponding to the density of Q. So, and if you see the if you focus on like where the red dots are, so there are two red dots here and one red dot here. So those are the areas where you know, we have like, so Q has some positive density, and so P is positive. P has a positive density in the region where we, you know, we see a lot of blue points, which is in the towards the left of this plot. So now if we could you know, like form an, if we could draw an arbitrary function f which has a very high value where like the blue curve is high and a very low value where the red curve is high, then if we you know, if we could find such a function, then that sort of indicates that the blue and the red curves are very different from each other, right? Because if they were very overlapping, then it would have been difficult to find such a black curve which is high in regions where blue is high, and low, very low, where regions where red is high, right? So if your x1 to xn and y1 to yn are very well mixed, then your blue curve and your red curve will overlap each other, right? So in that sense, we will say that, yeah, like the distribution P is close to distribution Q. But if that is not the case, then you know, you will possibly find out like examples of the black, like the curve here shown in black, which is high where P is high, and it is very low where Q is high. So what this black function is doing is, black function is actually like obtaining a very high value. So black function, let's say it is called a witness function and is represented by G. So then this integral of or the expectation of G with respect to P minus the expectation of G with respect to Q, that is very high, right? Because when P is high, your G is very high, and where Q is high, your G is negative. So since this is a difference, so this overall value is very high for such a witness function G. And how well of a witness function can be obtained, it then signifies or represents that, like, how far P and Q are from each other. So in that sense, like this supremum where G belongs to calligraphic G of integral of GS times PS minus QS is called a is an integral, is a proper distance measure in the space of the distributions. And this G is a class of functions which are called witness functions. So that's basically the intuition behind integral probability metrics. So in a sample sense, there is something called a maximum mean discrepancy. So which can be calculated for a sample and kind of gives us a sample estimate of this IPM. So as you can imagine, like for arbitrary distribution P and Q, like calculating this supremum over an arbitrary class, even if this class is a class of linear functions or like continuous like C01 functions. So even then, this calculating the supremum is not feasible for most cases. So we need some way to calculate this in a sample sense. And maximum mean discrepancy allows us to do that. So maximum mean discrepancy is an estimate can be used as a so depending on what this class of functions G is, so the IPM is equivalent to calculating the maximum mean discrepancy. So what is maximum mean discrepancy? So similar to the previous example, so let's say you were drawing samples from distribution P and drawing samples from distribution Q. And you are trying to understand that like whether the P and Q are very different from each other or not. So think of that like, so your P is a images from images of dogs, and Q are sort of like images of fish, right? So now to understand that like whether your fish and dogs are very different, if the images are very different or not. So what you can do is you can find out like what's the intra-similarity of dog-to-dog images. So typically we will see that yeah, like dog-to-dog images are very similar to each other, and we can find out like what's the similarity of fish-to-fish images. So we will see that like yeah, so mostly fishes are similar to each other, but and we can also calculate like what's the similarity of a fish-to-dog image, right? And similarly like so by symmetry, like your fish to dog image similarity is equal to your dog to fish similarity. So now if we like so if the dog to dog similarity is very high and your fish to fish similarity is very high and your dog to fish similarity is low, then like you will kind of conclude that these two like your dog images distribution and your fish image distribution is very like not similar to each other at all. And that's what this is doing. So like so K here is a kernel which kind of represents like what's the similarity between xi and xj. And like so we add up, like we take like what's the average over these MC2 points over the P distribution, the data points are from the distribution of P for xi, xj. Similarly, we calculate like what's the intra similarity for data points drawn from distribution Q. And then we subtract it from the like what's the across group similarities. So if the across group similarities are very low, then this MMD is very high. So we're showing that P and Q are very further apart. Whereas if the across similarities are comparable to the within group similarities, then this MMD-PQ is low, showing that P and Q are close to each other. So once we have obtained an MMD estimate of this IPM, then we can just plug it in this equation and like then try to minimize this upper bound, and that will like sort of reduce the sum of this EF plus E or the upper bound of the EF plus ECF. So that's basically the main technical or the main theory behind the Tarnet kind of an approach. And so the balance, so this can be actually be implemented through a neural network and like an appropriate loss function. So what we do is we take the confounder X as an input and T also as an input, and we obtain like a high dimensional representation or actually a lower manifold representation of the confounders. So let's represent it by phi. And so what we do is we perform this IPM matching or this IPM like reduction for this representation layer. And for each of the uh, treatment types, like t equals 1 and t equals to 0, we also predict like what's the factual factual outcome, which is y1 and y0. So the factual outcomes help us in with this alpha times EF part, and the beta times IPM part is calculated by this from this representation layer. So in this way, we can form like we can like create an architecture of a neural network, which we can train by backpropagating the loss from both the IPM and the factual losses to like learn both the representation, like so the representation is balanced. And then like at the inference time, we can just pass a forward pass through the two head outcome networks to predict like what is y1 and y0 for every data point. And then we can take a difference of them, or we can just use them, we use y1 and y0. So note that like this also, as opposed to the subclassification and IPW estimate, like this is a way of getting the individual treatment effects, because we can perform like at the time of inference, we can perform the forward pass for every individual data points. So we finally move on to one more interesting algorithm, which is called the causal forest, so which is an extension of random forests. And in this model, in this methodology, what we, so in a random forest, we would split such that like we can obtain the maximum information gain, or like we can obtain the maximum amount of homogeneity across the two nodes. Like that's the choice of the split feature and the split threshold. So in causal forest, what we want to do is we want to maximize the difference of the observed gate. So that's like the criteria for choosing the split. So for example, in this case, like if we could split according to the age, like we split like young households and old households and calculate the observed gate for these two groups, then that, so we like if this partitioning gives like the highest average gates, then like this is the optimal partition according to the causal forest algorithm. And this can be, like we can prove that this algorithm produces consistent estimates of the treatment effect. So for example, like if we had a more mixed kind of a grouping, so like if this group had like some young, some old, then the gate difference would have been lower in this case, and also like lower in the other case as well. So the overall split maximization, so the maximization of the gate based on the splits would not have happened. So overall, then we discussed like two classical techniques and two modern techniques. So the classical techniques were the IPW and the subclassification methods, and the modern were the TARNet, the balancing neural network, and the causal forest algorithms. So we finally also know about some other popular methods. So one is based on explicit matching method. So this methodology is again has similarities and is inspired by the domain adaptation methods. We have a meta-learner based techniques, which are T-learners, S-learners, and X-learners. And we also have like a seminal paper in the last, like I think in 2017, which is known as double machine learning. So that's also another popular methodology for estimating treatment effects. So overall, in this, so at this point, we will sort of wrap up like learning about the treatment effects. And so overall, we learned about what's the necessity for causal inference, what are the things that we were trying to estimate through causal inference, specifically treatment effects, and what frameworks or what assumptions do we need to make to be able to estimate these treatment effects. And we looked into some like classical and some modern methodologies for estimating the treatment effects. So like the presentation will also contain like all the references to the papers and the related works, and also a list of like tools and public data sources that you can use to develop or experiment with various algorithms. Thank you.